Before the first minute of this video ends, the sun will already seem small. Far beyond our solar system, astronomers have discovered stars so enormous that they challenge everything people imagine about size in the universe. Some are so vast that if placed where the sun is today, they would stretch far beyond the orbit of Jupiter. But the most surprising part is that the biggest star known may be even larger than scientists once believed. Tonight, follow a journey across unimaginable distances as the true scale of the cosmos slowly comes into view. If enjoying these relaxing space documentaries, please take a moment to like this video, subscribe to Cosmic Bedtime Stories, and settle in for an extraordinary voyage through the largest stars ever discovered. The narrative begins at the outermost limit of astronomical observation, where the concept of a cosmic boundary is not a physical wall, but a horizon defined by light and time. This boundary is known as the observable universe, and it represents the farthest distance from which light has had enough time to reach Earth since the beginning of cosmic expansion. Everything beyond this horizon remains unseen, not because it does not exist, but because its light has not yet arrived, or may never arrive due to the ongoing expansion of space. Within this framework, astronomers rely on electromagnetic radiation, especially visible light radio waves and other wavelengths, to construct a coherent map of distant regions. The observable limit is therefore shaped by both the age of the universe and the finite speed of light, creating a layered structure of visibility that becomes progressively dimmer and older as distance increases. At the largest scale, space appears nearly uniform, filled with galaxies distributed in vast filaments and voids. These structures form the cosmic web, a pattern that emerges from subtle variations in the density of matter in the early universe. Over billions of years, gravity amplifies these variations, drawing gas and dust into denser regions where galaxies eventually form. Yet even this immense structure is only a partial view, a thin cross-section of a far larger reality that cannot be directly accessed. The limits of observation are not sharp in a geometric sense, but gradual in a temporal sense, because looking farther into space is equivalent to looking further back in time. Light from distant galaxies carries information from epochs when the universe was significantly younger, cooler and denser than it is today. Within this observable boundary, astronomers measure distance using a combination of redshift and standard candles. Redshift occurs because the expansion of space stretches the wavelength of light travelling through it, shifting it toward the red end of the spectrum. The greater the redshift, the further away and earlier in time the light originates. Standard candles, such as certain types of supernovae, provide reference points for estimating distances because their intrinsic brightness is well understood. By comparing observed brightness to expected brightness, distances can be inferred even across billions of light years. These methods together allow a three-dimensional reconstruction of the universe within the observable horizon, although always with increasing uncertainty as distances grow. The boundary itself is often described as the surface of last scattering a region formed when the universe was approximately 300,000 years old. At that time, the universe cooled enough for electrons and protons to combine into neutral atoms, allowing light to travel freely for the first time. Before this transition, the universe was opaque, filled with a dense plasma that scattered photons continuously. The release of this radiation created a faint background glow that still fills all of space today. This cosmic background radiation provides a snapshot of the earliest structure of the universe, revealing tiny fluctuations that would later grow into galaxies and clusters. Although this radiation marks a kind of observational limit, it is not a physical edge but a temporal one representing the earliest moment that light can still be detected. Beyond this early radiation field lies a deeper conceptual boundary shaped by cosmic expansion. As space continues to expand, some regions of the universe recede from observation faster than light can travel toward Earth due to the stretching of space itself. This means that, even though light travels at a constant speed locally, the space it moves through can expand in such a way that distant regions become permanently inaccessible. Over immense timescales, more galaxies cross this horizon of disconnection, gradually leaving the observable universe. This process is slow on human timescales, but significant on cosmological scales, reshaping the visible structure of the universe over billions of years. Within this context, the observable universe is not a static sphere but a dynamic region defined by changing boundaries. Its radius is commonly estimated at about 46 billion light-years in all directions, but this value reflects the current extent of visibility rather than a fixed physical size. The difference between distance and look-back time becomes crucial in understanding this scale, because light from the most distant observable objects began its journey when those objects were much closer in space than they are today. As a result, the observable universe represents a layered history rather than a simple geometric volume. At this outermost level of observation, matter appears in its most diffuse and ancient forms. Hydrogen and helium dominate the composition of intergalactic space remnants of the earliest nucleosynthesis processes. These light elements drift in vast thin regions between galaxies, forming the raw material from which future structures may emerge. Even at this scale, gravity continues to operate slowly, drawing matter together, though the timescales involved are far longer than the current age of stars. The distribution of this primordial material reflects the earliest conditions of the universe, preserved across time as a faint but persistent structure. The observable boundary therefore serves as the starting point for all astronomical understanding. It defines not only what can be seen, but also what can be inferred about the universe beyond direct observation. Every measurement of distance, every map of galaxy distribution, and every analysis of cosmic background radiation depends on interpreting signals that arrive from this edge of visibility. As instruments become more sensitive and techniques more refined, this boundary expands slightly, revealing new layers of distant space. However, it always remains fundamentally constrained by the speed of light and the age of the universe, ensuring that the horizon remains a persistent feature of cosmic observation. In this outer region, the concept of size itself becomes abstract, because distance and time merge into a single framework of observation. A galaxy observed at extreme distance is not seen as it is now, but as it was billions of years ago, potentially no longer existing in the same form. This means that the observable universe is a living record of transformation, capturing stages of cosmic history in a single expanding sphere of light. The boundary is therefore both a limit and memory, preserving the earliest accessible moments of structure formation, while continuously shifting as new light arrives from deeper space. At the beginning of systematic stellar cataloguing, the night sky is treated as a structured field rather than a scattered collection of lights. Early observers record positions of bright points, using careful visual alignment building maps that divide the sky into recognizable patterns that remain stable over human lifetimes. These early mappings do not yet describe physical nature, but they establish a framework of position and repetition, allowing later generations to compare changes with greater precision. The outermost layer of this system is the apparent sky itself, where stars appear fixed relative to each other over short timescales, creating the illusion of permanence while Earth moves through space. As observational tools improve, the introduction of telescopes expands the number of visible stars far beyond unaided vision. the sky becomes densely populated with faint points of light, each requiring systematic recording to avoid confusion. Astronomers begin to organize stars by location, brightness, and motion, forming early catalogues that attempt to bring order to what appears infinite. These catalogues serve as reference systems, allowing repeated observation of the same objects under changing conditions of atmospheric clarity, seasonal positioning, and instrumental improvement. The process gradually shifts astronomy from descriptive skywatching to structured measurement. With increasing precision, brightness becomes a central parameter. Stars are ranked by apparent magnitude, a scale that reflects how bright they appear from Earth, rather than how luminous they truly are. This distinction introduces an important separation between observation and physical reality. A dim star may be intrinsically powerful but distant, while a bright star may be relatively close but less energetic. This ambiguity motivates further refinement of measurement techniques, including improved distance estimation methods that begin to reveal the true scale of stellar distribution in space. As cataloguing becomes more sophisticated, motion across the sky is also recorded. Some stars exhibit slow shifts relative to background objects known as proper motion. These movements reveal that the star field is not fixed but dynamic over long timescales. The recognition of motion introduces a deeper understanding of spatial depth, as nearby stars tend to move more noticeably than distant ones. This provides a way to separate layers of the stellar environment, moving from a flat sky map to a three-dimensional structure extending outward from the solar system. The development of spectroscopy marks a shift from external mapping to internal inference. By splitting starlight into its component colors, astronomers observe patterns of absorption lines that correspond to specific elements present in stellar atmospheres. These spectral signatures allow classification of stars based on composition and temperature, even without direct physical access. The outer layers of stars become readable as chemical records revealing hydrogen, helium, and heavier elements in varying proportions. This method transforms stars from points of light into physical objects with measurable properties. Through spectral classification, stars are grouped into categories based on temperature and surface characteristics. Hotter stars display strong blue and ultraviolet emission, while cooler stars emit more red and infrared light. These differences are not merely visual, but reflect underlying physical conditions within stellar atmospheres. The classification system reveals that stars are not uniform objects, but occupy a continuous range of states, determined by mass, temperature, and evolutionary stage. This framework becomes central to modern astrophysics, linking observation to internal structure. As understanding deepens, distance measurement techniques improve, allowing catalogues to include not only position and brightness, but also spatial placement within the galaxy. Parallax measurements based on the apparent shift of a star's position due to Earth's orbit provide direct geometric distances for relatively nearby stars. This method establishes a baseline scale for the universe of stars, anchoring more distant estimates. With this foundation, astronomers begin to construct a three-dimensional map of the local stellar environment, revealing clusters, associations, and sparse regions of interstellar space. Within these catalogues, patterns emerge that suggest underlying physical relationships. Stars of similar temperature and brightness often occupy related positions in diagrammatic representations, revealing correlations between luminosity and surface temperature. These relationships imply that stars evolve over time, moving through different stages depending on their mass and internal processes. Although these evolutionary paths are not directly visible, they are inferred from large populations of stars observed at different stages of their lifetimes. The catalogue becomes not just a record of positions, but a record of stellar life cycles distributed across space, At deeper levels of analysis, stellar catalogues begin to reveal large-scale structure within galaxies. Stars are not randomly distributed but concentrated in spiral arms, clusters and globular formations. These structures reflect gravitational organization on galactic scales shaped by the combined mass of billions of stars and interstellar material. The catalogued data allows astronomers to trace the shape and rotation of the galaxy itself, placing individual stars within a broader dynamic system that evolves over hundreds of millions of years. As observational precision continues to improve, the distinction between catalogue and physical model begins to blur. Each recorded star becomes not just a point in space, but a data structure containing information about composition, motion distance, and evolutionary state. The accumulation of such data creates a layered understanding of the stellar population, moving from simple visual identification to complex physical interpretation. This progression establishes the foundation for all later studies of stellar size, mass, and internal structure, which will depend on the accuracy and depth of these early catalogues. By the end of this foundational phase, the night sky is no longer perceived as a flat dome of scattered lights, but as a vast structured system extending in all directions, filled with objects that vary in scale, composition, and history. The cataloguing process transforms uncertainty into measurable order, allowing astronomers to begin comparing stars not only by appearance, but by intrinsic properties. This shift marks the transition from observation to physical understanding, preparing the framework for deeper analysis of how stars grow, evolve, and reach extreme sizes far beyond initial expectations. With stellar catalogues established as structured records of position, brightness, and motion, the focus of astronomical study shifts toward the physical scale of stars themselves. The concept of size is not directly observable for most distant stars because they appear as unresolved points of light even through the most powerful telescopes. Determining their true dimensions therefore requires indirect reasoning based on measurable properties such as luminosity, temperature, and distance. These measurements form the outer framework from which physical size is inferred rather than directly seen. The first step in estimating stellar size involves understanding brightness as a measurable quantity of energy output. Apparent brightness describes how much light reaches an observer, while intrinsic brightness, or luminosity, describes how much energy a star emits in total. To move from one to the other, distance must be known with reasonable accuracy. Once distance is established, the inverse square relationship between brightness and distance allows astronomers to calculate how much light is actually being emitted. This relationship forms a foundational bridge between observation and physical reality, linking the outer appearance of a star to its internal energy processes. Temperature plays an equally important role in determining stellar size. Stars emit radiation across a spectrum that depends on surface temperature, with hotter stars producing more high-energy light and cooler stars producing more low-energy light. By analyzing the distribution of light across different wavelengths, astronomers can estimate surface temperature. This temperature, combined with luminosity, allows the application of physical laws governing radiating bodies. Stars behave approximately like blackbody emitters, meaning their radiation follows predictable patterns based on temperature and surface area. This connection makes it possible to infer size indirectly, since a larger surface area at a given temperature produces greater total luminosity. At this stage of understanding, stellar size is no longer treated as a direct visual measurement, but as a derived quantity. The outer observation of brightness becomes a gateway into internal structure. A star that appears extremely bright may either be very close, very large, or extremely hot, and only careful separation of these factors allows accurate interpretation. This complexity introduces uncertainty, especially for distant stars, where measurement errors in distance propagate into large uncertainties in luminosity and therefore size. Despite this, statistical methods applied across large populations of stars help refine general relationships between temperature, brightness, and radius. One of the key tools in this process is the relationship between luminosity, surface temperature, and radius. When a star's luminosity and temperature are known, its radius can be calculated using established physical laws governing radiating spheres. This does not require direct imaging of the star's edge, but instead relies on how much energy must be emitted from a surface of a given temperature to produce the observed brightness. In this way, size becomes a mathematical inference grounded in measurable quantities rather than a visual observation. As this method is applied across different types of stars, clear patterns begin to emerge. Some stars with relatively low surface temperatures still emit enormous amounts of energy, implying extremely large surface areas. These stars are classified as giants or supergiants, representing stages of stellar evolution in which size expands dramatically. Conversely, very hot stars can appear bright despite smaller physical size, demonstrating that luminosity alone cannot determine scale. The separation of these variables becomes essential for constructing a coherent understanding of stellar dimensions. The refinement of distance measurement strengthens these calculations. Parallax observations for nearby stars provide a baseline, while more distant stars require indirect methods such as comparison with standard candles or cluster fitting techniques. Each improvement in distance accuracy reduces uncertainty in derived size, gradually sharpening the overall map of stellar dimensions. This process reveals that stars occupy a wide range of sizes, from relatively compact main sequence objects to enormous expanded stars whose outer layers extend far beyond initial expectations. At the same time, observational technology continues to improve angular resolution, allowing some of the nearest and largest stars to be partially resolved. Interferometry, which combines light from multiple telescopes, makes it possible to measure the angular diameter of certain nearby stars. When combined with known distance, angular diameter can be converted into physical radius. This provides one of the most direct methods of size estimation, though it remains limited to relatively close and large objects due to current technological constraints. Within this framework, the concept of stellar radius becomes a central physical parameter. It represents the distance from a star's center to the outer layer from which most visible light is emitted. However, this outer layer is not always sharply defined, especially in large and diffuse stars. In some cases, the outer regions gradually fade into surrounding space, making the exact boundary difficult to determine. This introduces ambiguity into size measurements, as different observational methods may yield slightly different radii depending on how the outer atmosphere is defined. Despite these uncertainties, consistent patterns emerge when large samples of stars are analyzed. Stars of similar mass and composition tend to follow predictable relationships between size and temperature over their lifetimes. These relationships form the basis of stellar evolutionary models, which describe how stars change in size as they consume nuclear fuel and adjust internal pressure balances. Although the internal processes are not directly visible, their effects are encoded in observable properties such as brightness and surface temperature. As understanding deepens, it becomes clear that stellar size is not static but evolves over time. A star may begin its life in a relatively compact state, then expand significantly as internal conditions change. This expansion is not uniform but depends on complex interactions between gravity radiation pressure and nuclear fusion processes occurring in the core. These internal dynamics remain hidden beneath the surface, but their influence is reflected in the outward dimensions that can be inferred from observation. The study of stellar size therefore represents a transition from external measurement to internal inference. What begins as catalogued points of light becomes a set of physically characterized objects with measurable radii masses and energy outputs. Each improvement in observational technique refines this understanding, reducing uncertainty and revealing greater diversity in stellar structure. Within this framework, size is not simply a geometric property, but a reflection of deep physical processes operating within each star. By the end of this stage of analysis, stars are no longer merely points of light in a catalogue, but extended physical systems whose dimensions can be estimated with increasing precision. The concept of scale becomes central, revealing that some stars are far larger than early observations suggested. This realization sets the stage for deeper exploration into the most extreme stellar forms, where size and structure reach limits that challenge initial expectations about how large a star can become. With stellar size now established as a derived physical property, attention turns to the relationship between brightness and reality, where observation can diverge from actual structure. The outermost layer of understanding is still based on light reaching distant observers, yet that light carries only partial information about the full physical system. Brightness, as it appears from Earth, is influenced by distant surface temperature and intervening material, making it an incomplete indicator of true stellar nature. The process of separating these effects becomes essential for interpreting what a star actually is, rather than how it merely appears. At large distances, light spreads out across expanding spheres of space, reducing intensity in a predictable way. This geometric dilution means that even extremely powerful stars can appear faint if they are far enough away. Conversely, nearby stars with modest energy output may appear bright simply because their light has not dispersed significantly. This creates an observational layer in which apparent brightness is heavily shaped by spatial position rather than intrinsic power. The challenge for astronomers is to remove this positional effect in order to recover true luminosity. Interstellar space adds another layer of complexity. Between stars, thin clouds of gas and dust absorb and scatter light, altering both intensity and color. Blue light is more easily scattered than red light, causing distant stars viewed through dusty regions to appear redder and dimmer than they truly are. This reddening effect can lead to misinterpretation of temperature and size if not properly corrected. By measuring how light is shifted across wavelengths, astronomers can estimate how much material lies along the line of sight and adjust their calculations accordingly. This correction reveals a more accurate picture of the star's intrinsic properties. The concept of luminosity becomes central in distinguishing reality from appearance. Luminosity represents the total energy emitted by a star in all directions, independent of the observer's location. It is a property of the star itself rather than its environment. However, determining luminosity requires precise knowledge of distance and careful correction for interstellar absorption. Without these adjustments, brightness alone cannot reliably indicate physical scale. This separation between observed brightness and true energy output is a key step in understanding stellar diversity. Surface temperature further complicates the relationship between brightness and reality. A star's color provides information about its temperature, with hotter stars emitting more energetic radiation. However, temperature alone does not determine total brightness. A small but very hot star can appear extremely bright in certain wavelengths, while a larger but cooler star may emit more total energy across the full spectrum. This distinction reveals that brightness in a single observational band is not sufficient to characterize a star's true output. Only by integrating radiation across all wavelengths can a complete measure of luminosity be obtained. The role of distance estimation remains critical in resolving these differences. Without accurate distance measurements, even carefully corrected brightness values cannot yield reliable luminosities. Methods such as parallax provide direct geometric distances for nearby stars, while more distant objects require indirect approaches based on known stellar populations. Each method introduces its own uncertainties, which propagate into final calculations of brightness and size. Despite these challenges, repeated observations and cross-calibration between methods gradually improve accuracy. In some cases, brightness variations over time provide additional insight into stellar nature. Certain stars exhibit regular or irregular changes in brightness due to internal pulsations or external interactions. These variable stars can serve as important tools for distance measurement when their intrinsic variability patterns are well understood. By comparing observed variation periods with known physical relationships, astronomers can estimate luminosity more accurately. This technique helps bridge the gap between apparent brightness and true energy output across vast distances. The distinction between optical appearance and physical structure becomes even more important when examining extended stellar atmospheres. Some large stars possess outer layers that are diffuse and gradually thinning rather than sharply bounded. In such cases, brightness may originate from a wide region rather than a clearly defined surface. This makes it difficult to assign a precise edge or radius based solely on visual observation. The outer glow of such stars can extend far into space, blending with surrounding material and further complicating measurements. Modern observational techniques help resolve some of these challenges by using multiple wavelengths of light. Infrared observations can penetrate dust that obscures visible light, while ultraviolet measurements reveal high-energy processes near stellar surfaces. By combining data across the electromagnetic spectrum, a more complete understanding of stellar structure emerges. This multi-wavelength approach reduces the distortion caused by any single observational band, allowing more accurate reconstruction of intrinsic properties. As understanding improves, it becomes clear that brightness is not a single fixed property, but a composite of multiple factors. Distance, temperature, composition, and surrounding environment all contribute to what is observed from Earth. Separating these factors requires careful modeling and repeated measurement, transforming raw observation into physical interpretation. This process reveals that what appears simple in the night sky is in fact the result of complex interactions between light and space. Through this refined understanding, astronomers begin to recognize that some of the brightest objects in the sky are not necessarily the largest or most massive. Instead, brightness often reflects a combination of proximity and temperature rather than size alone. This realization is essential for avoiding misinterpretation when comparing different stars. Without correcting for these effects, the apparent hierarchy of brightness would not reflect the true physical hierarchy of stellar structure. The separation between appearance and reality ultimately reshapes how stellar systems are understood. Brightness becomes a starting point rather than a conclusion, guiding deeper investigation into underlying properties. Each correction applied to observational data brings the physical model closer to reality, revealing the true diversity of stellar forms hidden beneath the surface of light. In this way, the study of brightness becomes a process of peeling away layers of distortion to reveal the underlying structure of stars as they truly exist. By the end of this stage, it is clear that observation alone is insufficient to understand stellar nature. Only through careful separation of contributing factors can true size and energy output be determined. This understanding prepares the framework for examining the most extreme stellar classes, where brightness and size diverge dramatically, and where the limits of stellar structure begin to emerge in ways that challenge earlier assumptions. The relationship between brightness and physical reality clarified attention shifts toward the most extreme categories of stars, where standard patterns of size and luminosity begin to stretch beyond early expectations. The outermost layer of this exploration remains the visible sky, but within it certain stars stand out not only for their brightness, but for their unusual behavior across time. These objects are not rare in absolute number, yet they represent brief and unstable phases in stellar evolution, making them difficult to observe in detail. Their significance lies in the way they redefine the upper boundaries of stellar scale. Among these extreme objects, supergiant stars form a distinct class defined by their immense luminosity and expanded outer structure. These stars are not simply larger versions of ordinary stars, but represent advanced evolutionary stages in which internal balance shifts dramatically. The outer layers of such stars expand outward, while the core continues to generate energy through nuclear processes. This imbalance between outward radiation and inward gravity produces a structure that is vast in size but relatively low in density compared to smaller, more compact stars. The classification of supergiants emerges from observational patterns in brightness and spectral characteristics. These stars often exhibit strong spectral lines indicating complex atmospheric compositions, including heavier elements formed through advanced stages of nuclear fusion. Their spectra reveal not only temperature, but also the presence of extended outer atmospheres, where material is loosely bound and slowly moving outward. This gives supergiants a diffuse appearance, even when they are among the most luminous objects in their galaxies. At this stage of stellar evolution, mass plays a critical role in determining final structure. Stars significantly more massive than the Sun evolve differently due to stronger gravitational compression in their cores. This leads to higher internal temperatures and faster nuclear reaction rates. As hydrogen becomes depleted in the core, fusion shifts to outer layers, causing the star to expand dramatically. The outer envelope responds to these changes by increasing in radius while decreasing in density, creating a vast stellar atmosphere that can extend far beyond what earlier models of stars had predicted. The scale of supergiant stars is not easily comparable to smaller stellar types because their outer boundaries are diffuse and variable. Unlike compact stars with well-defined surfaces, supergiants often have extended atmospheres where gas gradually transitions into surrounding space. This makes the exact definition of their radius dependent on observational method and wavelength. Different instruments may detect different outer layers, leading to varying estimates of size. Despite this uncertainty, all measurements agree that these stars occupy the upper extreme of known stellar dimensions. Within this class, red supergiants represent a particularly large and cool subset. Their surface temperatures are lower than those of hotter stars, but their enormous surface areas compensate for this in terms of total energy output. The outer layers of these stars are often convective, meaning that large-scale motion carries energy from the interior toward the surface. This convective motion contributes to irregular brightness variations as different regions of the surface change over time. The resulting structure is dynamic and constantly shifting rather than stable and uniform. The apparent color of red supergiants is influenced by their cooler surface temperatures, which shift emitted light toward longer wavelengths. However, this color does not reflect simplicity or weakness, but rather an advanced stage of stellar evolution. Beneath the visible surface lies a complex internal structure where multiple layers of fusion may occur simultaneously in different regions. These layered processes contribute to the star's immense energy output, even as the outer surface appears relatively cool compared to hotter, smaller stars. Despite their size, supergiant stars are not long-lived in cosmic terms. Their high mass leads to rapid consumption of nuclear fuel, shortening their lifespan significantly compared to smaller, more stable stars. This rapid evolution means that supergiants are often observed in transitional states, making each example valuable for understanding late stages of stellar development. Their instability is a direct consequence of the delicate balance between gravity and radiation pressure operating within their expanded structures. Observationally, supergiants present both opportunities and challenges. Their brightness makes them visible across vast distances, allowing them to be studied even in other galaxies. However, their extended atmospheres and variability complicate precise measurement. Changes in brightness over time must be carefully monitored to distinguish between intrinsic variability and external effects such as dust or intervening material. This requires long-term observation and multi-wavelength analysis to construct accurate physical models. In terms of spatial scale, supergiant stars challenge intuitive understanding of size. If placed at the center of a planetary system, their outer layers could extend beyond the orbits of inner planets in some cases. Yet this expansion does not correspond to increased density or solidity. Instead, it represents a gradual thinning of stellar material as it extends outward. The concept of a solid boundary becomes less meaningful, replaced by a gradient of decreasing density that eventually merges with interstellar space. The study of supergiant stars therefore reveals that stellar size is not a fixed or sharply bounded property, but a dynamic outcome of internal and external forces. Their immense scale is the result of evolutionary processes that redistribute mass and energy over vast distances. These stars serve as a bridge between ordinary stellar forms and the most extreme states of matter in the universe, marking a critical stage in the life cycle of massive stars. By examining these objects, astronomers begin to understand that the upper limits of stellar size are not strictly defined by simple geometric constraints, but by the complex interplay of fusion radiation and gravity. This realization opens the path toward exploring even more extreme and unstable stellar structures, where variability and expansion reach levels that challenge earlier assumptions about how large a star can become. At this stage of exploration, attention moves deeper into the structure of the most expanded stars, where the outer layers are no longer clearly defined surfaces, but gradually thinning regions of gas extending far from the core. These regions form what is described as stellar atmospheres, though the term atmosphere here does not resemble the thin, sharply bounded layer surrounding a planet. Instead, it refers to a vast diffuse envelope, where density decreases smoothly with distance from the center. The outermost portion blends almost imperceptibly into interstellar space, making the true boundary difficult to determine with precision. In red supergiant stars, this extended atmosphere becomes one of the most defining features of the entire structure. The outer layers are cool relative to the core, yet they occupy enormous volumes. This cooling is not a sign of inactivity, but a consequence of energy being distributed over a much larger surface area. As energy from the interior spreads outward, it loses intensity, leading to lower surface temperatures, even while the total energy output remains extremely high. This balance between expansion and cooling defines the visual and physical character of these massive stars. Within these outer layers, motion is not uniform. Instead, large convection cells carry energy from the interior toward the surface. These cells can span a significant fraction of the stellar radius, creating regions where hot material rises while cooler material sinks. This movement produces an uneven surface appearance where brightness varies across different regions. Over time, these variations contribute to observable changes in overall luminosity, making the star appear unstable when viewed from great distances. The atmosphere of a red supergiant is not static but continuously changing. Material is gradually lost from the outer layers due to weak gravitational binding. As particles in the upper atmosphere gain enough energy, they escape into surrounding space, forming slow-moving stellar winds. These winds carry gas and dust outward, enriching the interstellar medium with heavier elements produced within the star. This process of mass loss plays an important role in the chemical evolution of galaxies, even though it occurs gradually over long timescales. The density within these outer regions is extremely low compared to the core. In many cases, the outer atmosphere is so diffuse that it approaches conditions similar to near vacuum. Despite this, it remains optically thick enough in certain wavelengths to obscure deeper layers. This means that what is observed as the surface of the star is not a solid boundary, but a region where light becomes less able to escape freely. Different wavelengths of light emerge from different depths, making the concept of a single surface dependent on how the star is observed. Temperature gradients within the atmosphere are also significant. The outermost layers are relatively cool, while regions closer to the interior become progressively hotter. This gradient influences the spectrum of emitted light with different wavelengths, providing information about different depths. By analyzing these spectral signatures, astronomers can reconstruct a layered understanding of the star's structure, revealing how energy moves outward through complex interactions of radiation and matter. In some regions of the extended atmosphere, dust formation can occur. As material cools and expands, certain elements condense into small solid particles. These dust grains absorb and scatter light, contributing further to the complexity of observed brightness and color. The presence of dust also affects how much material is eventually lost to space, since radiation pressure acting on dust grains can help drive stellar winds outward. This interaction between radiation gas and dust creates a dynamic environment that evolves continuously over time. The outer atmosphere is also influenced by pulsations within the star. As internal pressures fluctuate, the star can expand and contract in slow cycles. These pulsations propagate outward, affecting the density and temperature of the atmosphere. In some cases, these changes are large enough to cause noticeable variations in brightness when observed from Earth. However, these variations are not uniform or predictable in simple terms, as they depend on complex internal processes that are not directly visible. Despite the immense size of these stellar envelopes, they are not stable structures. The balance between gravitational attraction and outward pressure is delicate, and small changes in internal energy production can lead to significant shifts in atmospheric structure. This instability contributes to the relatively short lifespan of supergiant phases in stellar evolution. Over time, these outer layers may be lost entirely, revealing deeper internal regions, or leading to dramatic end stages of stellar collapse. The extended atmosphere also serves as a transitional zone between the star and its surrounding environment. Material expelled from the star does not immediately disperse into space, but forms surrounding shells or clouds of gas. These structures can persist long after the star has changed its evolutionary state, leaving behind a record of past mass loss events. In this way, the atmosphere of a supergiant is not only part of the star itself, but also a contributor to the broader galactic environment. Observationally, these extended regions present significant challenges. Because the outer atmosphere lacks a sharp boundary, different instruments may interpret the size of the star differently depending on wavelength sensitivity. This leads to variations in estimated radius and structure, highlighting the importance of multi-wavelength observation. Infrared measurements often reveal cooler outer material, while visible light captures hotter inner layers. Together, these perspectives form a more complete picture of the star's true extent. Through this understanding, the concept of a stellar surface becomes less like a physical boundary and more like a transition zone defined by changes in transparency. The outer atmosphere is not a fixed layer, but a continuously shifting region shaped by energy flow, material loss, and internal motion. This realization further expands the understanding of stellar size, showing that the largest stars are not defined by solid edges, but by diffuse evolving structures that extend far into space. By the end of this stage, it becomes clear that the apparent size of a star is deeply influenced by how its outer layers interact with light and surrounding space. The true physical extent of these stars cannot be captured by a single measurement, but must instead be understood as a range shaped by dynamic atmospheric conditions. This sets the stage for examining the limits of stellar mass and structure, where physical constraints begin to define how far such expansions can realistically go. At this stage of understanding, the exploration moves inward from the extended stellar atmosphere to the underlying constraints that govern how large a star can physically become. The outermost view still presents stars as vast, luminous structures, but beneath this appearance lies a framework defined by mass gravity and the balance of forces within stellar interiors. These factors determine not only how stars form and evolve, but also how far they can expand before structural limits begin to dominate their behavior. Stellar mass is the primary factor that controls the entire life cycle of a star. It represents the total amount of matter contained within the object and sets the strength of gravitational force acting inward toward the center. Higher mass leads to stronger gravitational compression, which in turn increases pressure and temperature in the core. These conditions accelerate nuclear fusion, causing the star to produce energy at a much higher rate. This relationship between mass and energy output forms the foundation for understanding why massive stars behave so differently from smaller ones. However, mass alone does not determine size directly. Instead, size emerges from the balance between inward gravitational force and outward pressure generated by radiation from nuclear fusion. When these forces are in equilibrium, the star maintains a stable structure. If radiation pressure becomes stronger, the outer layers expand. If gravity dominates, the star contracts. This constant balance defines the dynamic equilibrium that governs all stellar forms, from small dense objects to the largest known stars. As stars become more massive, their internal conditions change significantly. The core temperature rises sharply, allowing fusion reactions to proceed at much faster rates. This increased energy output pushes outward against gravity, leading to expansion of the outer layers. In some cases, this expansion becomes extreme, producing stars with radii hundreds or even thousands of times larger than the Sun. Yet this expansion is not unlimited because it is constrained by the ability of the star to maintain structural stability under its own gravity. Radiation pressure plays a key role in this process. As energy generated in the core moves outward, it exerts force on the surrounding material. In highly massive stars, this outward force can become strong enough to significantly inflate the outer envelope. However, this same process also leads to instability, as small fluctuations in energy production can cause large-scale changes in structure. The star becomes sensitive to internal variations, making its outer layers more prone to expansion and loss. There is also a physical limit to how much mass a star can accumulate before radiation pressure begins to overpower gravitational confinement. This limit is not fixed as a single value, but depends on composition temperature and internal structure. When a star approaches this upper boundary, its outer layers become increasingly unstable, and mass loss through stellar winds becomes more pronounced. These winds carry away material into surrounding space, effectively regulating the star's growth and preventing indefinite accumulation of mass. In very massive stars, this process of mass loss becomes a defining feature of their evolution. Strong radiation fields drive material away from the surface, gradually reducing total mass over time. This loss of mass affects the internal balance of forces, altering the star's structure and evolutionary path. As a result, the most massive stars may not retain their initial mass for long periods, since their own energy output actively works against gravitational retention. The relationship between mass and size is therefore indirect and mediated through complex internal processes. A star with greater mass does not simply become larger in a straightforward way. Instead, it undergoes a series of structural adjustments that determine how its energy is distributed and how its outer layers respond. In some cases, this leads to significant expansion, while in others, it results in relatively compact but extremely hot and luminous configurations. Observational data supports the existence of an upper range of stellar masses, beyond which stable, long-term structures difficult to maintain. Stars near this range often exhibit strong variability, rapid mass loss, and complex atmospheric behavior. These characteristics indicate that they are operating near physical limits imposed by the balance of radiation and gravity. While exact boundaries are still refined through ongoing observation, the general principle remains consistent. There is a threshold beyond which stellar structure becomes increasingly unstable. The concept of stellar size must therefore be understood in relation to these mass-driven constraints. The larger stars are not simply those with the greatest amount of material, but those in which internal forces allow for extensive expansion of outer layers without complete structural collapse. This delicate balance produces the extreme supergiant and hypergiant stars observed in the universe, which represent temporary phases in the evolution of very massive stellar systems. As these massive stars evolve, they move through stages where mass distribution changes significantly. Fusion processes shift between different elements, altering the internal energy output and therefore the balance of forces. Each stage can result in expansion or contraction, depending on how energy is produced and transported within the star. These transitions are not smooth, but often involve instability, further contributing to variability in size and brightness. Ultimately, stellar mass defines both the potential and the limits of stellar size. It determines how much energy can be generated, how strongly gravity can confine material, and how the outer layers respond to internal changes. The larger stars exist within a narrow range where these competing forces remain in temporary balance. Outside this range, stars either fail to expand significantly or become unstable and lose mass rapidly. By the end of this stage, it becomes clear that the question of how large a star can become is not answered by a single measurement, but by understanding the continuous interaction between mass gravity and radiation pressure. These forces shape every stage of stellar evolution and define the boundaries within which even the most extreme stars must exist. This foundation prepares the exploration for deeper analysis of instability in massive stars, where these forces begin to fluctuate in ways that produce dramatic structural changes. At this stage of inward progression, attention moves from the general constraints of stellar mass toward the internal conditions that destabilize very massive stars. The outer appearance still suggests vast luminous structures, but beneath the surface lies a constantly shifting balance of pressure, temperature, and energy flow. In extremely massive stars, this balance becomes increasingly difficult to maintain, and small internal variations can produce large structural responses throughout the entire star. Inside these stars, the core operates as the primary energy source through nuclear fusion. Hydrogen is converted into helium, releasing energy that travels outward through layers of stellar material. As hydrogen becomes depleted, fusion shifts to heavier elements in successive stages, each requiring higher temperatures and producing different energy outputs. This layered fusion structure creates a complex internal environment where different regions contribute differently to the overall energy balance. The outward flow of energy from the core is not instantaneous. It moves through dense material, interacting repeatedly with particles through absorption and re-emission processes. This slow transport creates a delay between energy generation in the core and energy release at the surface. In very massive stars, this delay becomes significant enough to affect stability, because changes in the core do not immediately reflect at the outer layers. This lag can amplify internal fluctuations, contributing to instability. Radiation pressure plays a central role in maintaining structural support. As energy moves outward, it exerts force on surrounding material, counteracting gravity. In extremely massive stars, this outward pressure becomes so strong that it approaches the limits of gravitational confinement. When these two forces nearly balance, even minor changes in energy production can shift the equilibrium, causing expansion or contraction of large regions within the star. Temperature variations within the interior also contribute to instability. Fusion reactions are highly sensitive to temperature, meaning that small increases in core temperature can lead to significantly higher energy output. This feedback effect can accelerate energy production in localized regions, causing uneven distribution of pressure. As a result, some parts of the star may expand while others contract, creating complex internal motion patterns. These motions are not uniform but occur on multiple scales. Large convective currents can transport energy from the interior toward the outer layers, while smaller turbulent flows mix material within localized regions. In very massive stars, convection can extend over significant fractions of the stellar radius, creating large-scale circulation patterns that influence surface behavior. These movements contribute to variability in brightness and structure observed from a distance. As instability increases, the outer layers of the star become more responsive to internal changes. The envelope expands and contracts in response to shifts in energy flow, sometimes producing observable pulsations. These pulsations are not random, but reflect underlying physical processes within the core and intermediate layers. However, because the system is highly complex, these variations may appear irregular when viewed over time. Mass loss becomes increasingly important in this unstable regime. Strong radiation fields and surface disturbances can eject material from the outer layers, forming stellar winds that carry mass away from the star. This loss of material reduces gravitational binding, further altering the balance between inward and outward forces. In some cases, mass loss can significantly change the evolutionary path of the star, effectively reshaping its future structure. In the most extreme cases, instability can lead to episodic eruptions where large amounts of material are expelled over relatively short periods. These events are driven by internal energy buildup and sudden releases of pressure within the outer layers. Although dramatic in scale, they are part of a gradual process of structural adjustment rather than isolated catastrophic events. Over time, repeated episodes of mass loss can significantly reduce the star's mass and alter its observable properties. The instability of massive stars is closely linked to their proximity to physical limits of radiation support. When energy output becomes comparable to the gravitational force holding the star together, the system enters a delicate state where equilibrium is easily disrupted. This condition does not produce immediate collapse, but instead leads to ongoing fluctuations in size, brightness, and structure. The star becomes dynamically active, with its outer layers responding continuously to internal changes. Despite this instability, such stars can persist for significant periods in astrophysical terms. Their evolution is governed by slow but continuous changes in the internal composition and energy generation. Each stage of fusion introduces new conditions that reshape the internal balance, gradually pushing the star toward later evolutionary phases. These transitions are not abrupt but occur over extended timescales, during which instability remains a defining characteristic. Observationally, these stars often appear variable in brightness and spectral properties. Changes in surface conditions reflect deeper internal processes, allowing astronomers to infer the presence of complex internal dynamics. However, direct observation of these processes is not possible, so interpretations rely on models that connect observable variations to underlying physical mechanisms. Ultimately, instability in massive stars is not a sign of failure, but a natural consequence of their extreme physical conditions. The same forces that allow them to achieve enormous size also make them sensitive to internal fluctuations. This sensitivity defines their behavior and limits their stability, shaping their evolution toward later stages, where even more extreme forms of stellar structure emerge. By the end of this stage, it becomes clear that the largest stars exist in a state of continuous adjustment, where internal forces are constantly rebalancing against gravity. This dynamic instability prepares the path toward examining specific extreme examples where these processes become visible through observational records of the most massive and variable stars known. At this stage of exploration, attention moves from theoretical limits and internal instability toward observed examples of the most extreme stars currently known. The outer framework remains the same observational universe, where stars appear as points of light shaped by distance, brightness, and spectral signature. Within this framework, certain stars stand out because their inferred sizes approach or exceed the highest expected limits established by models of stellar structure. These objects are not defined by a single measurement, but by a convergence of observational methods that together suggest extraordinary scale. The process of identifying extreme stars begins with surveys of brightness across the sky. Large-scale observations collect data on luminosity and spectral type, allowing astronomers to isolate candidates that appear unusually bright for their distance. However, brightness alone is insufficient, so these candidates are subjected to further analysis, involving temperature estimates and distance refinement. Only after combining these factors can an estimate of physical size be derived, revealing which stars occupy the upper range of known stellar dimensions. Among the most well-studied extreme stars are red supergiants whose radii extend far beyond typical stellar scales. These stars are identified through their cool surface temperatures and high luminosity, which together imply vast surface areas. Observational data suggests that some of these stars could extend to sizes comparable to or exceeding the orbit of Mars, or even beyond, depending on the exact method of measurement. However, these values are not fixed because the outer layers of such stars are diffuse and difficult to define with precision. The challenge in measuring these extreme objects lies in their extended atmospheres. Unlike compact stars with clearly defined photospheres, red supergiants possess outer regions where gas density gradually decreases with distance. This means that the edge of the star is not a sharp boundary but a transition zone where light becomes progressively more difficult to trace. Different wavelengths of light probe different depths within this atmosphere, leading to varying estimates of radius depending on observational technique. Interferometric measurements provide some of the most direct size estimates for nearby supergiants. By combining light from multiple telescopes, astronomers can resolve the angular diameter of these stars, converting it into physical size using distance measurements. These observations confirm that certain stars reach extraordinary radii far exceeding the size of typical main sequence stars. However, even these precise methods are limited by the irregular and changing nature of stellar atmospheres. One of the most notable characteristics of these extreme stars is their variability. Many exhibit changes in brightness over time driven by internal pulsations and large-scale convective motion. These variations are not minor fluctuations but can represent significant shifts in energy output and surface structure. As a result, the estimated size of such stars may also change, depending on the phase of observation, adding another layer of complexity to measurement. In addition to red supergiants, other categories of extreme stars include luminous blue variables and hypergiants. These stars are often more massive and hotter than red supergiants, but can also reach large radii during unstable phases of their evolution. Luminous blue variables in particular are known for dramatic changes in brightness and occasional mass ejection events that reshape their outer layers. These processes make them difficult to classify consistently, as their properties can change significantly over relatively short timescales. The most extreme candidates often exist in transitional stages of stellar evolution. They are not permanent configurations but temporary phases in which internal and external forces are in dynamic balance. During these phases, stars may expand significantly before losing mass or transitioning into different evolutionary states. This transient nature means that the largest observed sizes may represent brief moments in a star's life, rather than stable long-term structures. Uncertainty remains a defining feature of all measurements at this scale. Because outer stellar atmospheres are diffuse and irregular, defining a precise boundary is inherently difficult. As a result, different studies may report slightly different values for the same object depending on methodology and assumptions. Despite this variation, the overall conclusion remains consistent. Certain stars reach sizes that push the limits of what stellar structure can support. The study of these extreme objects also highlights the importance of multi-wavelength observation. Infrared measurements often reveal cooler, more extended material that is not visible in optical wavelengths, while optical data captures hotter inner regions. By combining these datasets, astronomers construct a more complete model of stellar structure, reducing uncertainty in size estimates. This integrated approach is essential for understanding objects whose atmospheres extend far into surrounding space. As observational techniques improve, previously known size estimates are occasionally revised. Some stars initially thought to be among the largest are later found to be smaller after improved distance measurements or better modeling of their atmospheres. Conversely, new observations sometimes reveal candidates that exceed earlier expectations. This ongoing refinement reflects the evolving nature of astronomical measurement, rather than inconsistency in physical reality. Ultimately, the largest known stars represent the intersection of extreme physical conditions and observational limits. They exist in a regime where mass radiation and instability combine to produce vast and diffuse structures that challenge precise definition. While models provide a framework for understanding their behavior, direct measurement remains limited by the nature of their extended atmospheres and variable conditions. By the end of this stage, it becomes clear that the upper range of stellar size is not defined by a single definitive object, but by a group of extreme candidates whose properties overlap and vary. These stars serve as benchmarks for understanding the limits of stellar expansion, preparing the framework for deeper examination of how such vast structures are detected and interpreted despite their inherent uncertainty. At this stage of analysis, the focus shifts from identifying extreme stellar candidates to the deeper difficulty of measuring their true extent. The outer observational layer remains dependent on light collected across vast distances, But in these cases, the light originates from regions where structure is no longer sharply defined. The concept of a stellar edge becomes increasingly ambiguous as the outer layers of these stars gradually fade into surrounding space without a clear boundary. This creates a fundamental limitation in determining exact size. The challenge begins with the nature of diffuse stellar atmospheres. In extreme stars, the outer regions are composed of thin gas that decreases in density with distance from the core. There is no solid surface or abrupt transition, only a gradual reduction in material until it merges with the interstellar environment. Because of this, any measurement of radius depends on selecting a reference point within a continuous gradient, rather than identifying a physical edge. Different observational techniques naturally choose different reference levels, leading to variation in reported sizes. One common approach defines the stellar radius based on the point where the atmosphere becomes transparent to visible light. This layer, often referred to as the photospheric region, represents the depth from which most observable radiation escapes. However, this boundary shifts depending on wavelength, because different frequencies of light can penetrate to different depths. As a result, the apparent size of the star changes depending on whether it is observed in visible infrared or other parts of the electromagnetic spectrum. Infrared observations often reveal more extended structures than visible light, because cooler outer material emits strongly at longer wavelengths. These observations can significantly increase estimated stellar size compared to optical measurements alone. However, even infrared data does not capture the full extent of the tenuous outer envelope, which may continue far beyond detectable emission levels. This introduces an inherent uncertainty in defining the true physical boundary of the star. Another complication arises from distance measurement. Even small uncertainties in distance can produce large errors in calculated radius, especially for extremely large stars. Because angular diameter measurements must be converted into physical size using distance, any imprecision in parallax or indirect distance methods directly affects final results. This sensitivity means that improving distance estimates can significantly alter the perceived scale of some of the largest known stars. Variability further complicates measurement. Many of these extreme stars are not stable objects but change in brightness and structure over time. Pulsations in the outer layers can cause expansion and contraction cycles, altering the apparent radius, depending on when observations are made. In some cases, these changes occur over periods of months or years, meaning that size measurements represent snapshots rather than fixed properties. This time dependence adds another layer of complexity to interpretation. Interferometric techniques provide some of the most precise measurements available, but even these methods face limitations when dealing with irregular and dynamic atmospheres. By combining light from multiple telescopes, interferometry can resolve very small angular scales, allowing partial imaging of stellar surfaces. However, for extremely diffuse stars, the outer regions remain difficult to constrain because the signal becomes weak and uneven. This leads to uncertainties in defining the outermost detectable layer. The presence of surrounding material also affects observational clarity. Many extreme stars are embedded within clouds of gas and dust that have been expelled from their outer layers. This material can scatter and absorb light, altering the apparent brightness and shape of the star. In some cases, this surrounding envelope becomes so extensive that it is difficult to separate the star itself from its immediate environment. The boundary between star and surrounding medium becomes observationally blurred. Modeling plays an essential role in addressing these uncertainties. By combining physical laws with observational data, astronomers construct theoretical profiles of how density and temperature vary within stellar atmospheres. These models allow estimation of where certain reference points might lie even when direct observation is not possible. However, these models depend on assumptions about internal structure and mass loss, meaning that they carry their own uncertainties. As understanding improves, it becomes clear that the concept of a single definitive stellar radius is often an approximation rather than an exact value. For extreme stars, size is better represented as a range defined by different observational methods and physical interpretations. Each method highlights a different aspect of the star's structure, from the dense inner regions to the diffuse outer envelope extending into space. This realization shifts the focus from seeking a precise boundary to understanding the distribution of matter around the star. The outer layers are not simply an extension of the core, but a dynamic region shaped by ongoing energy flow and mass loss. In this sense, the size of a star is not a fixed measurement, but a description of how far its influence extends into surrounding space under different observational conditions. By the end of this stage, it becomes evident that measuring the largest stars is not just a technical challenge, but a conceptual one. The absence of a clear boundary forces a redefinition of what size means in astrophysical terms. Rather than a single number, it becomes a layered interpretation shaped by physics observation and the limitations of measurement itself. This understanding prepares the transition toward examining hypergiant variability, where instability further complicates the already uncertain structure of these extreme stellar objects. At this stage of the inward progression, attention focuses on stars that do not maintain even the loosely defined stability of supergiants, but instead fluctuate across multiple physical scales in ways that reflect deep internal instability. These hypergiant stars represent some of the most dynamically active objects in stellar evolution, where size, brightness, and structure are continuously shifting rather than settling into equilibrium. The outermost observational layer still records light as the primary source of information, but that light now carries the imprint of rapid and complex internal change. Hypergiant stars are identified not by a single defining property, but by a combination of extreme luminosity, high mass, and strong variability. Their brightness can change noticeably over relatively short astronomical timescales, indicating that their outer layers are responding to internal disturbances. Unlike more stable stars where energy output remains relatively steady, hypergiants exhibit irregular fluctuations that reflect shifts in pressure balance and energy transport within their interiors. These variations make them difficult to classify precisely, as their observed properties can differ depending on the moment of observation. The outer envelopes of hypergiant stars are highly extended and loosely bound. Gravity at these outer layers is weak compared to the outward pressure generated by intense radiation from the interior. As a result, material in the outer regions can be easily disturbed, leading to large-scale atmospheric motion. These motions are not smooth or uniform, but occur in complex patterns influenced by convection pulsation and radiation-driven flows. The surface appears turbulent with regions of expansion and contraction occurring simultaneously across different areas. Internal pulsations play a central role in shaping the behavior of hypergiant stars. These pulsations are driven by changes in opacity and energy flow within the stellar interior. As energy moves outward, it can become temporarily trapped in certain layers, causing localized increases in pressure. When this energy is released, it can lead to sudden expansion of outer regions. These cycles create repeating but irregular patterns of variability, affecting both brightness and apparent size over time. The relationship between brightness and structure in hypergiants is particularly complex. Changes in luminosity may reflect not only variations in energy output, but also changes in the effective surface area from which light is emitted. As outer layers expand, the surface area increases, altering the total amount of light radiated, even if the internal energy generation remains constant. Conversely, contraction can lead to increased surface temperature and shifts in spectral output. This interplay makes it difficult to separate intrinsic luminosity changes from structural changes. Mass loss is a defining feature of hypergiant evolution. Strong radiation fields and surface instability drive powerful stellar winds that carry material away from the star at high rates. In some cases, these winds are continuous, while in others they occur in episodic bursts that eject large quantities of gas into surrounding space. This ongoing loss of mass gradually alters the gravitational balance of the star, influencing its long-term stability and evolutionary path. The expelled material forms extended nebulae that record the history of these outflows. The outer regions of hypergiants are often surrounded by complex envelopes of gas and dust. These structures are formed from previously ejected material and remain gravitationally or radiatively influenced by the central star. As light passes through or reflects off this surrounding material, it can be scattered or absorbed, complicating observational measurements. In some cases, what is observed as part of the star may actually be extended circumstellar material rather than the stellar surface itself. Temperature variations across the surface of hypergiants further contribute to their irregular appearance. Large convection cells transport energy unevenly, leading to regions of differing brightness and color. Hotter areas emit more energetic radiation, while cooler regions appear dimmer and redder. These variations are not static but shift over time as internal flows evolve. The result is a constantly changing surface pattern that reflects deep internal motion rather than a stable outer boundary. Because of these dynamic processes, the concept of stellar size becomes especially fluid in hypergiants. The outer layers may expand significantly during periods of increased energy output and contract during quieter phases. This means that radius measurements depend strongly on the timing of observation. Unlike more stable stars where size can be treated as approximately constant, hypergiants require a time-dependent interpretation of structure. Observational techniques capture different aspects of this variability. Long-term monitoring reveals cycles of brightness change, while high-resolution imaging can detect surface irregularities and asymmetries. Spectral analysis shows shifting absorption features that correspond to changing atmospheric conditions. Together, these methods provide a multi-layered view of a star that is in constant flux, rather than a static object with fixed properties. Despite their instability, hypergiants play an important role in understanding the upper limits of stellar structure. Their behavior demonstrates how extreme mass and energy output interact to produce conditions where equilibrium is only temporarily maintained. Each phase of expansion and contraction provides insight into the balance of forces operating within the most massive stars. These observations help define the boundary between long-term stability and rapid evolutionary transition. Over time, the continued mass loss and internal instability of hypergiants lead them toward later stages of stellar evolution. The outer layers become increasingly diffuse, and the core structure evolves toward more compact configurations. Although these processes occur over extended timescales, they represent a pathway toward the eventual end stages of massive stars. Hypergiants therefore occupy a transitional position between the largest stable stellar forms and the final outcomes of stellar collapse. By the end of this stage, it becomes evident that hypergiant stars do not represent fixed points in the classification of stellar size, but rather dynamic systems in continuous change. Their extreme variability challenges simple definitions of scale and reinforces the idea that the largest stars in the universe exist in states of ongoing transformation rather than static equilibrium. This understanding prepares the framework for examining how surrounding material contributes to perceived size in the next stage of exploration. At this stage of inward exploration, attention shifts from the star itself to the material that surrounds it, where the perceived size of the larger stellar objects is shaped not only by the star's own structure, but also by the environment it creates. The outermost observational layer still relies on incoming light, yet that light is now influenced by extended clouds of gas and dust that originate from the star's own history of mass loss. These surrounding structures form a complex boundary region, where the distinction between star and environment becomes increasingly blurred. Around massive evolved stars, expelled material accumulates over long periods, forming circumstellar envelopes that can extend far beyond the immediate stellar surface. This material is not static, but slowly moves outward, driven by stellar winds and radiation pressure. As it expands, it cools and becomes increasingly diffuse, eventually blending into the interstellar medium. However, during this transitional phase, it remains detectable and can significantly influence observational measurements of size and brightness. The presence of dust within these envelopes plays a crucial role in shaping how the star is perceived. Dust grains form when heavier elements in the cooling outflow condense into solid particles. These grains interact strongly with light, absorbing shorter wavelengths and re-emitting energy in the infrared. This process alters the apparent brightness of the central star, often making it appear dimmer in visible light, while revealing extended structure in infrared observations. As a result, different wavelengths can produce different impressions of the same object. The distribution of circumstellar material is often uneven, reflecting the history of mass loss events. Rather than forming a smooth spherical shell, the expelled material can appear clumpy, asymmetric, or layered. These irregularities arise from variations in stellar wind strength, pulsations in the outer layers, and localized ejection events. Each episode of mass loss leaves behind a distinct structure that gradually expands outward, creating a layered record of the star's evolutionary history. In some cases, the surrounding envelope becomes so extensive that it rivals or exceeds the size of the star's visible photosphere. This creates a situation where the apparent boundary of the star depends heavily on observational wavelength and sensitivity. Optical observations may only capture the inner brighter regions, while infrared or radio measurements reveal much larger extended structures. Determining which of these regions should be considered part of the star itself becomes a matter of definition rather than direct measurement. Interstellar dust and gas in the surrounding environment also contribute to observational complexity. As light travels through these regions, it can be scattered in multiple directions, creating halos or diffuse emission around the star. This scattered light can be misinterpreted as part of the stellar atmosphere, especially when resolution is limited. Careful modeling is required to separate genuine stellar emission from reflected or reprocessed light in the surrounding medium. The interaction between stellar radiation and surrounding material is not passive but actively shapes the structure of the envelope. Radiation pressure can push dust and gas outward, accelerating mass loss and influencing the geometry of the outflow. In some cases, this results in bipolar or asymmetric structures, where material is preferentially ejected along certain directions. These directional flows further complicate the interpretation of size, as the star's influence extends unevenly into space. Over time, the accumulated circumstellar material forms expanding shells that record past episodes of instability and mass loss. These shells can persist long after the conditions that created them have changed, providing a layered archive of stellar behavior. When observed at different distances from the central star, these shells reveal a history of repeated structural changes, each contributing to the overall extent of the surrounding environment. The presence of this extended material also affects temperature measurements. Dust and gas absorb energy from the star and re-emit it at different wavelengths, creating thermal gradients that extend far from the central source. This redistribution of energy means that the region influenced by the star can extend well beyond the visible boundary of the photosphere. However, this influence does not necessarily correspond to physical stellar material, adding further ambiguity to definitions of size. In extreme cases, the circumstellar envelope can become optically thick in certain wavelengths, meaning that light from the inner star is partially or fully obscured. In such situations, observers may primarily detect emission from the surrounding material rather than the star itself. This inversion of visibility complicates attempts to measure the true size of the central object, as the observed structure may be dominated by expelled matter rather than the stellar surface. Despite these complexities, circumstellar environments provide valuable information about the history and behavior of massive stars. By analyzing the composition, gravity, and distribution of this material, astronomers can infer past mass loss rates and identify periods of instability. These surrounding structures therefore serve as indirect records of the star's evolution, even when the central object itself is partially obscured. The distinction between star and environment becomes increasingly conceptual at this stage. The outer boundary is no longer defined solely by the star's internal structure, but by the interaction between radiation, matter, and motion in the surrounding space. Size becomes a layered concept encompassing not only the central object, but also the region influenced by its energy output over time. By the end of this stage, it becomes clear that the perceived scale of the larger stars cannot be separated from their surrounding envelopes. The true extent of these systems is shaped by continuous exchange between stellar interiors and expelled material, creating environments that extend far beyond any simple geometric boundary. This understanding prepares the transition toward examining how revised interpretations of size emerge when all observational uncertainties and environmental effects are combined. At this stage of analysis, attention turns from individual observational challenges to the broader process by which scientific understanding of stellar size is continuously revised. The outer observational layer remains dependent on light distance and spectral interpretation, but the interpretation of that data evolves over time as measurement techniques improve. What once appears to be a definitive measurement is gradually refined, adjusted or reinterpreted as new methods reduce uncertainty and reveal previously unresolved structure. Early estimates of stellar size were often based on simplified assumptions, treating stars as uniform spheres emitting light evenly across their surfaces. Under this framework, luminosity and temperature provided a straightforward path to estimating radius. However, as observational precision improved, it became clear that many of the larger stars do not conform to these simplified models. Their atmospheres are extended, irregular, and variable, requiring more complex interpretations that account for gradients in density and temperature. One of the key drivers of revision in stellar size estimates is the improvement of distance measurement. Because physical radius depends directly on distance, even small corrections can significantly alter derived sizes. As techniques such as parallax measurement became more precise, and as space-based observatories reduced atmospheric distortion, many previously estimated stellar radii were recalculated. In some cases, stars once considered among the largest were found to be smaller, while others increased in estimated size due to revised distances. Another source of revision comes from improved modelling of stellar atmospheres. Earlier models often assumed sharp boundaries between the photosphere and surrounding space. Later observations revealed that these boundaries are gradual and wavelength dependent. As a result, newer models incorporate extended atmospheric layers and variable opacity, producing more nuanced estimates of where a star effectively ends. This shift changes the interpretation of size from a fixed boundary to a probabilistic region defined by observational criteria. Multi-wavelength astronomy has also played a major role in revising stellar size estimates. Observations across infrared, optical, ultraviolet, and radio wavelengths reveal different aspects of the same object. Infrared data often shows cooler, more extended regions that are invisible in optical light, while ultraviolet observations highlight hotter, more compact structures. Combining these data sets leads to more complete models, but also reveals discrepancies that require reconciliation. These differences contribute to ongoing refinement of size estimates. As data quality improves, some stars previously classified as extreme size candidates are re-evaluated. In certain cases, what appeared to be a single large star is revealed to be a binary system or a complex surrounding nebula. In other cases, improved resolution separates stellar emission from surrounding circumstellar material, reducing the estimated size of the central object. These revisions highlight the importance of distinguishing between intrinsic stellar structure and environmental effects. The process of revision is not limited to downward adjustments. New observations occasionally identify stars whose extended atmospheres or luminosity profiles exceed earlier expectations. These cases often involve highly evolved unstable stars with significant mass loss and complex surrounding envelopes. As observational techniques become more sensitive, previously undetected, outer layers can be revealed, expanding the estimated scale of these systems. The concept of stellar classification itself evolves alongside these measurements. Categories such as supergiant or hypergiant are refined as new data reveals greater diversity within each group. Boundaries between categories become less rigid, with continuous distributions of size, temperature, and luminosity replacing earlier discrete classifications. This reflects a broader shift in astrophysics toward understanding stars as part of a spectrum of physical states rather than fixed types. Uncertainty remains an inherent part of this process. Even with advanced instruments, certain aspects of stellar structure remain difficult to constrain. Extended atmospheres, irregular mass loss, and variable brightness introduce unavoidable variability into measurements. Rather than eliminating uncertainty, improved science often redefines it, narrowing some ranges while revealing new sources of complexity. This creates a dynamic understanding in which stellar size is always subject to refinement. The integration of theoretical models with observational data is central to this refinement process. Models of stellar structure provide predictions about how mass, energy, and radiation should behave under certain conditions. Observations test these predictions, and discrepancies between the two lead to model adjustments. Over time, this iterative process produces increasingly accurate representations of stellar behavior, but it also highlights the limits of direct measurement. In some cases, revision of stellar size estimates leads to broader changes in understanding of stellar evolution. If a star is found to be smaller or larger than previously thought, its inferred mass, age, and evolutionary stage may also need adjustment. This interconnectedness means that changes in one parameter can propagate through entire models of stellar populations, influencing how galaxies and star clusters are interpreted. Despite ongoing revisions, a consistent pattern remains: certain stars occupy the upper extremes of known size even when uncertainties are accounted for. These extreme objects define a practical boundary of stellar expansion under known physical conditions. While this boundary is not fixed in an absolute sense, it reflects the current understanding of how mass, radiation, and stability interact in the most massive stars. By the end of this stage, it becomes clear that stellar size is not a static measurement, but a continually evolving interpretation shaped by improving data, refined models, and deeper understanding of complex stellar environments. The larger stars known are therefore not only physical objects, but also subjects of ongoing refinement, representing the frontier where observation and theory continuously adjust to each other. This prepares the transition toward examining the most extreme candidate stars in greater detail, where current observations approach the limits of what can be reliably measured. At this stage of investigation, attention narrows to the most extreme candidate stars currently identified, where observational data approaches the limits of precision and interpretation becomes increasingly dependent on careful modeling. The outermost view remains anchored in collected light across vast distances, yet within that light lies evidence of structures so large and diffuse that their full extent is still being refined. These candidates are not defined by certainty, but by convergence of multiple measurement techniques that collectively suggest extraordinary scale. The identification of these extreme stars begins with surveys that scan large regions of the sky for unusually bright and cool objects. These initial selections are based on color and luminosity indicators that suggest large surface areas combined with relatively low surface temperatures. Such conditions often point toward expanded stellar envelopes, where energy is distributed across vast regions rather than concentrated in compact surfaces. However, these early indicators are only preliminary, requiring deeper analysis to confirm physical properties. Once candidates are identified, distance becomes the most critical parameter in determining true size. Even small revisions in distance estimates can significantly alter calculated radii, sometimes changing an object's classification within the hierarchy of stellar extremes. Space-based measurements and improved calibration techniques have reduced some of this uncertainty, but for the most distant or obscured objects, indirect methods remain necessary. These methods rely on comparisons with known stellar populations, introducing additional layers of inference. Among the most extreme candidates are red supergiants whose inferred radii place them among the largest known objects of their type. These stars exhibit cool surface temperatures and high luminosities, implying extremely extended surfaces. However, their outer layers are so diffuse that defining a precise boundary remains difficult. Observations often yield a range of possible values, rather than a single definitive size, reflecting the gradual transition between stellar atmosphere and surrounding space. In some cases, hypergiant stars are also included among the largest candidates, due to their extreme variability and episodic expansion phases. During periods of increased energy output, these stars can expand significantly temporarily, increasing their apparent size. However, these expansions are not permanent, and subsequent contraction or mass loss may reduce their size again. This variability means that any measurement represents a momentary state rather than a stable configuration. Infrared observations play a crucial role in identifying extended structures around these stars. Cooler outer layers and circumstellar material emit strongly in infrared wavelengths, revealing regions that are not visible in optical light. These observations often increase the estimated size of the star as they capture material extending far beyond the traditionally defined photosphere. However, distinguishing between stellar atmosphere and surrounding ejecta remains a persistent challenge. Interferometric techniques provide some of the most precise measurements available for nearby extreme stars. By resolving angular diameters with high precision, these methods allow conversion into physical size when combined with distance data. Even so, the irregular and dynamic nature of these stars introduces uncertainty into the interpretation of measured diameters. Surface asymmetries, pulsations, and localized brightness variations can all influence the observed signal. In addition to individual stellar properties, surrounding environments must also be considered. Many of the largest candidates are embedded within extended envelopes of gas and dust that result from long-term mass loss. These structures can extend far beyond the visible surface of the star and may contribute significantly to observed emission. Separating the central star from its environment requires careful modelling across multiple wavelengths and observational conditions. Despite these challenges, a consistent pattern emerges across multiple studies. A small number of stars repeatedly appear near the upper limits of known stellar size. While the exact ranking of these objects may shift with improved data, their general status as extreme cases remains stable. These stars serve as benchmarks for testing the limits of stellar structure under known physical laws. The uncertainty surrounding these candidates does not diminish their significance. Instead, it highlights the complexity of measuring objects at the edge of observational capability. Each refinement in data contributes to a more accurate understanding, but also reveals additional layers of structure and variability. As a result, the concept of largest known star becomes a dynamic classification rather than a fixed designation. These extreme candidates also demonstrate the importance of combining multiple observational methods. No single technique is sufficient to fully characterize their structure. Instead, size estimates emerge from the integration of spectral analysis, photometric measurements, interferometry, and environmental modelling. Each contributes a different perspective, and only through their combination does a coherent picture begin to form. At the boundary of current knowledge, these stars represent both physical extremes and methodological challenges. They exist in a regime where measurement precision is continually tested by the complexity of the objects themselves. As observational tools continue to improve, some candidates may be reclassified, while others may be confirmed as even larger or more complex than previously thought. By the end of this stage, it becomes clear that the largest known stars are not simply objects of fixed measurement, but evolving targets of scientific refinement. Their apparent size reflects both physical reality and the limits of current observational capability, placing them at the frontier of astrophysical understanding. This sets the stage for the final synthesis, where the implications of these extreme scales are considered in relation to human perception and the limits of intuition. At this final stage of exploration, attention turns from measurement and classification toward the broader implications of stellar scale itself, where the largest known stars challenge the limits of intuition and interpretation. The outer observational framework remains unchanged, still dependent on light travelling across vast distances, yet the meaning of that light has accumulated layers of complexity through every previous stage of analysis. What appears as a single point in the night sky is now understood as a deeply structured system shaped by mass radiation, instability, and surrounding material, all interacting across immense scales of space and time. The larger stars occupy a regime where familiar comparisons lose practical meaning. Their radii inferred through combined observational methods can extend to distances comparable to the orbits of inner planetary systems. Yet this comparison remains conceptual rather than literal, because these stars are not solid objects with rigid boundaries. Instead, they are extended regions of decreasing density, where material gradually thins outward into surrounding space. The idea of a surface becomes a statistical description rather than a physical edge defined by where light escapes rather than where matter ends. In this regime, the human tendency to visualize objects as discrete and bounded becomes insufficient. Stellar structures of extreme size do not conform to everyday categories of shape or solidity. They are dynamic systems where motion, radiation, and gravity continuously reshape the distribution of matter. Even over relatively short astronomical timescales, their outer layers can shift, expand, or contract in response to internal changes. This variability means that any static image of such a star represents only a moment within a long and evolving process. The observational limits that define these stars also shape their perceived scale. Because distance resolution and wavelength sensitivity all influence measurement, the largest stars are partially defined by the capabilities of available instruments. As those instruments improve, the interpretation of size evolves accordingly. This does not imply that the stars themselves change arbitrarily, but that the boundary between what is measured and what is inferred becomes progressively more refined. Each improvement reveals additional structure while also introducing new questions about definition and scale. Within this context, the concept of largest known star is best understood as a moving boundary of scientific knowledge. It reflects not only the physical properties of stellar objects, but also the current limits of detection and modelling. As observational methods become more precise, some previously estimated extremes are revised, while new candidates emerge that push the boundaries further. This continuous adjustment is a natural outcome of studying objects whose structures are inherently diffuse and variable. The extreme scale of these stars also highlights the role of time in defining structure. Light reaching observers from such distant objects carries information from different layers of the star's history, depending on how long it has taken to escape various regions. In this way, observation becomes a form of temporal reconstruction, where the present image is built from signals emitted at different depths and times. The star is therefore not seen as a single instant, but as a layered record of ongoing physical processes. Despite their immense size, these stars are transient in cosmic terms. Their instability, mass loss, and internal evolution ensure that they do not remain in extreme expanded states indefinitely. Over time, they transition into later stages of stellar evolution, shedding outer layers or undergoing collapse. This transient nature means that the larger structures observed are temporary configurations within longer evolutionary cycles, rather than permanent features of the universe. The difficulty of defining exact boundaries in such systems ultimately reflects a deeper principle that physical reality at extreme scales does not always align with simple geometric interpretation. Instead, structure is defined by gradients, probabilities, and interactions between forces rather than fixed edges. This requires a shift in understanding from solid forms to continuous distributions, where size becomes a matter of extent and influence rather than clear boundary. In the broader cosmic context, these stars represent only one stage in the ongoing transformation of matter under gravity and energy flow. Their immense scale is a consequence of physical laws operating consistently across the universe, producing regions of extraordinary expansion under specific conditions. Yet even at these extremes, the same underlying principles apply, linking them to smaller and more familiar stellar forms through continuous physical relationships. As the exploration concludes, the larger stars known do not stand as final endpoints, but as part of a continuum of structure that spans the universe. Their size, while extraordinary, is interpreted through a framework that integrates observation theory and the limitations of perception. They remain both physically real and conceptually fluid, defined as much by how they are measured as by what they fundamentally are. In the end, the understanding of these vast stellar systems reveals not only the scale of the universe, but also the boundaries of human comprehension. What begins as points of light in the sky expands into structures of immense complexity, shaped by forces operating over unimaginable distances and times. The larger star becomes not just an object of measurement, but a reflection of the methods used to perceive it existing at the intersection of physical reality and observational reach.